slowly than it is up here. And sorry, but the time is somewhere over here, going faster here, going faster here, going faster here. And so from Boston to here, looking at the Alice, we're saying, wow, we're going really fast. Okay, so this is really accelerating in a certain sense, we're trying to move very quickly for Alice. And so even though Bob looks back at Alice and says, hey, your clock is running slow, and they understand this acceleration phase in which her clock runs extra fast. And it makes up for the difference, so that in fact her clock at the end of the day reaches 10 instead of something less than 8. Okay? So we'll talk a little bit about that tomorrow. But you also have an exercise on this, which I think you'll have a lot of fun with. Yeah. Yeah. So what you're saying is, here's the sun, and here's the Earth, and Alice is on the Earth, and Bob is here traveling to that planet. Alice herself is accelerating. She's in motion around the sun, orbiting around the sun. So that's true, and the effect would be that, as we'll see a bit tomorrow, the effect would be that her time runs a tiny bit slower than it would if she were just floating in empty space, near the sun, at rest of the sun, floating in empty space. Okay, so actually, when we draw a picture like this, what we're imagining is really that Alice is at rest, just floating in empty space, and there are no massive objects around. There's not even the Earth or the sun. Okay, so it's really just someone floating in empty space and someone drifting in some rocket ship over here and then coming back, and everything happens in empty space. Yeah. Calendar box is slower. Travel is presented for time space, right? Space-time versus the trade-off for time space. So it is always not the shortest, it's always the longest. Okay, so if you look at this situation here, I want to just give you an example here. Pretty simple. Okay, so let me just take this straight line. So normally in Euclidean geometry, the shortest distance between 2 points, or a straight line is the shortest distance between 2 points. In Euclidean geometry, a straight line is the longest distance between 2 points. Okay, it has to do with that minus sign. Okay, let's take some examples here. So we start out, same numbers here, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so Alice just stays at rest on the Earth, and Bob takes a trip. In this case, the trip is someplace really close by, like the moon. Okay, so she takes a trip to the moon, and then he comes back. Okay, so he's got 10 days to do it, and so his speed is very small. He's got lots of time to take a trip a small distance, so his speed is very small compared to the speed of light. Okay, so there's going to be very little time dilation. Okay, so if this is 5 days for Alice, Alice says, yeah, Bob, it's going to be 5 days to get to the moon. On Bob's watch, it might be like 4.9 days. And then 4.9 here, so it'll be 9.8. So it'll be almost the same. Okay, very little time dilation. Okay, now if we go to in the same 10 days or 10 years or whatever, we go to a more distant object, okay, where we have to travel close to the speed of light. So the speed of light is 45 degrees, so we're going slightly less than the speed of light like that, and then slightly less than the speed of light back. Okay. So now, because the distance is so great, we have to cover a really great distance in just 5 years or whatever. We're going near the speed of light, there's a great amount of time dilation. So 5 years, so Alice says, yes, it'll be 5 years to get to that distant planet, but because of the huge time dilation on your watch, it might be, say, I don't say 1.5. Half a year back, so we're going 1. Okay, so Alice would have aged 10 years, and Bob would have aged just 1 year. Okay, and then the extreme case is basically moving at the speed of light. Okay, that's about the can't move at the speed of light, as photons can. Okay, so here is Alice. She watches a photon travel for 5 years away from her. So she puts on her flashlight. Photon travels out for 5 years. What distance does it cover? 20 years. Okay, so if this is 45, well that's 5, then that's 5. Okay, and what's the distance here? 0, because we calculate the distance by taking this 5 squared minus that 5 squared. So 5 squared minus 5 squared is just 0. Okay, so this distance here, as this line goes more and more towards 45, this distance gets shorter and shorter and shorter, because what we're doing is we're taking, to get the length of this in space-time, we take this squared minus this squared. As this thing approaches 5, that approaches 0. Okay, and that's the importance of the minus sign. That minus sign, we're going this squared minus this squared, and that minus sign results in this time dilation. This thing getting smaller and smaller and smaller, this distance getting smaller and smaller and smaller as you approach the speed of light. So basically, light rays have 0 length, okay, in any space-time. Okay, so if this is, say, our galaxy, and this is the Andromeda galaxy, and a photon gets sent out to the Andromeda galaxy, and from our point of view, how long does it take that photon to get there? So from our point of view, how long does it take a photon to click on a flashlight? How long would that photon take to get to Andromeda? So Andromeda is about 2.5 million light years. Okay, so we got 2.5 million years. Okay, but for this photon, the photon's going to go like that instantly, in 0 time. Okay, so the photon experiences, so the photon as it travels, and you think about cosmic microwave background photons, which came from, very early on in the universe. They've been traveling through empty space for 14 billion years, according to, our time. 16 to 1.